Today, I would like to talk about additional gates that we use in digital logic design. And this is the outline of my presentation. I will be talking about additional gates and symbols for these gates. I will be talking about the NAND gate. I'll talk about the NOR gate. If we have time, I'll talk about NAND, and NOR implementations. We'll continue, inshallah, this topic on Sunday. I'll talk about the exclusive OR gate, the exclusive NOR gate, and I'll talk about odd and even functions. So this will be a short presentation. Inshallah, we will finish it on Sunday. Now, already we know the AND gate, the OR gate, and the inverter. So already we have this symbol here for the AND gate. Notice that the output of the AND gate is X and Y. This is the OR gate, and the output is X or Y. And this is the NOT gate or the inverter, and the output is X prime. Now the NAND gate. So the meaning of NAND is not AND. So notice that the symbol of the NAND looks like the AND, but there is a small bubble, small circle appearing at the output of the NAND gate. So the output is not AND. It's not X and Y. That's the NAND gate. We also have the NOR gate. It looks like an OR, but there is this small circle appearing at the output that is going to invert the output of OR, so it becomes not OR. And this is the output of the NOR gate. It's not X or Y. There is also a buffer. Basically, the output is the same thing as the input. I'll talk about it later. This is not important to us now. I have the XOR gate, which is known as the exclusive OR, and the output is X XOR Y. And there is the exclusive NOR gate, which looks like the XOR, but it has this small bubble, small circle at the output. So it's not X XOR Y. And finally, there is the three-state gate. I'll not talk about the three-state gate now. I'll postpone it till later when I talk about something which is more advanced. I'll come back to it and talk about the three-state gate. So my focus in this presentation will be about the NAND gate, about the NOR gate, about the XOR, and the exclusive NOR. So why do we have these gates? Well, because of their low cost. It turns out that the cost of implementation is very low for the NAND and for the NOR. So today in the technology that we are using today, NAND and NOR gates can be implemented very efficiently in the hardware. The XOR and the exclusive NOR are more complex gates, but they are very useful, okay, when you would like to design arithmetic circuits. Yani, for example, you would like to design an adder. We need the XOR gate. We need the exclusive NOR gates. Okay, so we need these gates, okay, when we would like to do addition or subtraction. So for this reason, I talk about these gates because they are very important in design. Let me start first with the NAND gate. So NAND here means not AND. That's the meaning of NAND. It is not AND. And notice that we have a small bubble here, a circle appearing at the output of the AND gate. So it looks like AND, but it has an inverter at its output. So this is why it's called NAND or not AND. And the output of this NAND gate is not X and Y. That's the output. So it's not, it's the complement of X and Y. And using De Morgan's theorem, we know that not X and Y is not X or not Y. That will be the expression for the NAND gate. We can draw a truth table, okay, for the NAND gate. So notice that this is the function of the NAND. So the NAND will give me 1 if at least one of the inputs is a 0. Then you get a 1. If both inputs are 1 and 1, the AND will give me 1, the NAND will give me 0. So NAND is just the complement, okay, of the AND. So this is the truth table of the NAND gate. Now, when you think about it like this, as NAND gate is giving me as X prime or Y prime, you can think about it like an OR gate where the inputs here are inverted. So you can think about it as another symbol for NAND. So this will give you also X prime or Y prime. So this is also another way to obtain NAND. So by inverting the inputs and ORing, you will also get the same functionality as the NAND gate. So you can draw an OR gate with inverted inputs, and you can think about it as a NAND gate. Now, why do we have NAND gate? Because NAND itself can be implemented very efficiently in the CMOS technology, the complementary metal oxide semiconductor technology, which is used today in the design of digital circuits and digital systems. So it's very efficient, okay, in terms of chip area and speed. It's very fast. It only requires 4 transistors to implement a 2-input NAND gate. And for this reason, people like it. Circuit designers, they love the NAND gate. The NOR gate, okay, is the NOR means not or. That's the meaning of NOR. And again, we draw it as an OR gate, but we draw a small bubble circle here appearing at the output to invert. Okay, so the output is inverted, so it's not X or Y, and therefore we can write it as not X and not Y. That's the NOR gate. And if I would like to draw the truth table, this is the truth table for the NOR. So notice that if both inputs are 0 and 0, you get the output is equal to 1. If any of the input here is a 1, you get the output 0. Okay, in the case of the OR, you get the output 1, but in the case of the NOR, you get the output equal to 0. So that's just the complement of the OR gate. That's the NOR gate, okay? So not OR. Now, because we can write it as X prime and Y prime, you can think about it as an AND gate with 2 inverted inputs. Because if you have the inputs here are inverted, you get X prime and Y prime, the same thing that you get from a NOR gate. Now, this is the standard symbol for the NOR gate. This is not, okay? So when you draw the NOR gate, you should draw it as shown here. This is how you draw the NOR gate. You don't draw it as an AND with inverted inputs. But if you have an AND with inverted inputs, you get the same functionality as the NOR, okay? Now, similar to the NAND gate, the NOR gate is also implemented very efficiently in the CMOS technology. Again, 4 transistors only. So it's very efficient in terms of the area. It only requires a very small area on the chip, and also it has high speed. So it can actually switch, turn on and off very quickly, very fast. So this is a very fast gate. Now, the nice thing about the NAND and the NOR is that these gates are called universal gates. And the meaning of universal, they are called universal because they can be used to implement any Boolean function. So we can implement any Boolean function using only NAND gates. In fact, I can implement the inverter using NAND gate. I can implement AND using NAND gates. I can implement OR using NAND gates. So when I would like to think about a gate which is universal, it should implement any Boolean function using only NAND gates. If I only had NAND gates, I did not really have any other type of gate, this would be sufficient. You can implement any Boolean function using only purely NAND gates. Now, in order to prove that this gate is universal, I need to be able to implement NOT, AND, and OR using NAND gates. Let me start with the inverter. If you take X and NAND it with itself, okay, so it's not X, and this will give me X prime. So if I would like to draw a 2-input NAND gate, this will be a 2-input NAND gate. If I connect both inputs together and I connect it to my input X, then the output will be X prime. So here, I'm using a 2-input NAND gate as an inverter. طبعا, it's not really practical to use a 2-input NAND gate as an inverter, but we can if you want. If you did not really have an inverter, you only had 2-input NAND gates, we can use a 2-input NAND gate as an inverter. Of course, the inverter is smaller in size, okay, because it only has 1 input and can be implemented with 2 transistors, whereas the NAND gate requires 4 transistors. A 2-input NAND gate will require 4 transistors. So this is why we can use the NAND to implement NOT. We can also use okay, a NAND gate with inverted output to implement AND. Yani, for example, this is a NAND gate and this is an inverter. So when you take here the output of the NAND gates, when you take the complement of X NAND Y, so this will be the complement of X and Y, you get X and Y. Okay, so therefore you get the output here is X and Y. So basically, if you use a NAND gate and you take the output of the NAND and you invert it, you get X and Y, the same thing as an AND gate. So the inverter itself can be itself implemented using a NAND gate, and therefore you can just implement AND using a NAND gate followed by an inverter, and the inverter itself is NAND. So we can use the NAND gates to implement AND. We can also use NAND gates to implement OR. So here I'm going to use a NAND gate with inverted inputs. So this is my circuit here. Use a NAND gate, but at the inputs, use two inverters. One inverter for X and one inverter for Y. So this will give me X prime, this will give me Y prime. Now, when you take X prime NAND Y prime, this is the complement of X prime and Y prime. And when you apply De Morgan's theorem, you get X or Y. So basically, the output here will be X or Y, similarly to an OR gate. So we have used a NAND gate with inverted inputs to implement an OR gate, which means that the NAND can be used to implement an inverter. It can be used to implement an AND gate. It can be used to implement the OR gate. And these are the gates that I need to implement any Boolean function. So therefore, the NAND gate is sufficient to implement any function, any Boolean function. So for this reason, we say that the NAND gate is universal. Okay, is this clear? You have any question about this? NOR gate is also universal. The same thing that we have done for in the case of the NAND, we can do it in the case of the NOR. So if I would like to invert, if I take X NOR X, it's basically we complement here, we invert. So it's not X or X, which gives me X prime. So if I would like to draw a two-input NOR gate, that will be a two-input, or no, this is a NOR. And if I connect both inputs here, okay, and I use here my input X, then we get the output here, which is X prime. So I can use a two-input NOR gate. I can use it as an inverter because X NOR X will give me X prime. I can use a two-input NOR gate with inverted output to get X or Y. This is shown here. So use a NOR gate, a two-input NOR gate, followed by an inverter, and this will give me X or Y. So basically, we are inverting the output of the NOR, and this will give me OR. Okay, so the NOR will give me not X or Y. So when you invert and then you invert again, you get X or Y. Now, in the case of ANDing, we can use a NOR gate with inverted inputs, as shown here in the circuit diagram. So if you use two inverters at the inputs of a NOR gate, so notice that here I'm taking the NOR of X prime and Y prime. So when you take X prime NOR Y prime, then this will be not X prime or Y prime. That's the meaning, okay? And this will give me X and Y. So basically you get X and Y similar to an AND gate. So I can use the NOR gate with inverted inputs to implement AND. And this way we can say that the NOR gate is also universal. So we have seen two universal gates. We have seen the NAND gate is universal and the NOR gate is also universal. Do you have any question about this? Is this clear?
Yeah, it is clear.
Okay, so we are going to encounter now many designs in which we are going to use the NAND gate and the NOR gate in our design. So in addition to the AND, the OR, and the NOT, we can now use the NAND and the NOR. and we'll understand that these gates are very efficient and they can be implemented very efficiently, okay, using today's modern technology, using the transistors that exist today. We can implement these gates very efficiently. Now, one thing you should know about NAND and NOR, and that these two gates or operations are not associative. Okay, so these are non-associative operations. Remember the AND, the OR in the case of Boolean algebra? We know that AND is associative. We also know that OR is associative. So in the case of AND, OR, they are associative. But in the case of NAND, NOR, they are not associative. So you have to be very careful about them. So in the case of AND and OR, in the case of AND, if I take X and Y, take the result and Z, it's the same thing as X and Y and Z. So the order of the ending does not really matter in the case of AND. But in the case of NAND, NAND is not associative. So you have to be very careful when you are dealing with the NAND gate. Okay, so this is different. Okay, so the NAND is not the same thing as the AND. So for example, if you take X NAND Y between parentheses, and then the result NAND Z, if you take this, you get different result than X NAND Y NAND Z. So these will give you two different results. They are not the same. This is an indication that NAND itself is not associative. Yani, for example, if I would like to draw a circuit like this, so let me use here, let us say, a NAND gate. So this is X, this is Y. The output will be X NAND Y. And then I take here NAND Z. Okay, so this will be my first circuit here. And if I would like to draw the second circuit, I'm going to draw it like this. I'm going to draw here, okay, if I have the space, let me draw it below. So I'm going to draw another circuit. Here I'm going to draw Y NAND Z, and then I'm going to draw here a NAND gate. So this will be X NAND, Y NAND Z. So notice that the order here of the NANDing is different. These will give you different results. So these two circuits are not the same. If these were AND gates, they will produce exactly the same output. But because these are NAND gates, they will produce different outputs. So for example, in the case of X NAND Y NAND Z, let us use the properties of Boolean algebra. So X NAND Y is not X and Y. And then when I take it NAND Z, this is the expression. Now you can expand this expression. So not X and Y is X prime or Y prime. And then when you complement, when you end it with Z and then you complement, you get XY or Z prime. Okay, so that's what you get when you expand. So when you apply this knot to this knot, you get X and Y, and then you get or Z prime. That will be the final expression. So this expression will be the output of this first circuit. Okay. If you take X NAND between parentheses Y NAND C, and you expand it using the properties of Boolean algebra, it is X and, okay, not Y Z, and everything is complemented. So this is basically the expression for X NAND Y NAND Z. So notice that this is not X and this is not X Y Z. Okay, so this is Y NAND Z is not Y and Z, and this is X. This is the NANDing of this is for this final NAND here. I'm taking the complement of X and the complement of YZ. If you extend this, now this X prime here will give me X prime. This N becomes OR. The complement of YZ will give me YZ. So basically you get the final result is X prime or YZ. So this will be the output of this circuit, of the second one. So notice that the outputs are different. These are two different expressions. They are two different expressions. They will evaluate differently. Okay, so these are two different functions, and therefore the NAND operation is not associative, so the order of the NAND is important. It's very important to understand the order of the NAND. Let me clean up this mess. Let us do it for the NOR. The same thing for the NOR. NOR itself is not associative. So NOR operation is not associative. So if I would like to take X NOR Y NOR Z, it's not equal to X NOR Y NOR Z between parentheses. So if I would like to draw two different circuits, this is the NOR gate. This is here X, Y. So the out will be X NOR Y, and then NOR it with Z. If you do so, if you apply the properties of Boolean algebra, you get the final output as X or Y. Everything is ended with Z prime. So this will be the output of the first circuit. If you try to do it differently in a different order, if you take X NOR between parentheses Y NOR Z, you get a different expression. You get a different circuit that has a different expression. So you take here, you take X NOR, the result of Y NOR Z. So the order of the NORing is different. So for this reason, we can say that the NOR operation is not associative. Okay, is this clear? You understand this? I don't really have sufficient space to draw the other one, but now you understand the difference between. So you understand that the NOR operation is not associative. Questions? You are very quiet today, Yanni. Now this will take me to multiple input NAND and multiple input NOR gates. So what we have seen in the previous slide is what we have the 2-input NAND gate, and this is the 2-input NOR gate. Now we can have a 3-input NAND gate and a 3-input NOR gate. So in the case of the 3-input NAND gate, we take the complement, not X, Y, Z. In the case of the 3-input NOR gate, we take the complement, not here, between parentheses, X or Y or Z. Now notice that this 3-input NAND gate is not the same thing as having two NAND gates connected, as we have seen in the previous slide. Okay, so if you connect them, as shown here in this slide, and if I take here, let us say, X NAND Y, result NAND Z, the output of this will be X, Y, or Z prime. However, if you use a 3-input NAND gate, you get not X, Y, Z, which means X prime, or Y prime, or Z prime. You get a different output. So remember that this 3-input NAND gate is one gate. It's not two gates. Whereas here, we are using a sequence of two NAND gates, and this is why we got a different output. Here, this is one 3-input NAND gate. The same thing can be said for the 3-input NOR gate. It is just one gate, not a sequence of two NOR gates. You can also have a 4-input NAND gate. You can also have a 4-input NOR gate. So you can actually have more than two. You can have 3 or 4 or even more if you want. Okay. So remember that a 3-input NAND gate is a single gate. It is just one gate, not a combination of two 2-input gates. The same thing can be said about other multiple input NAND NOR gates. Right. So let me talk today about NAND implementation and NOR implementation. So if I have the following sum of product expressions, okay, F is equal to BD or A prime C D prime. So I call this a sum of products, okay, or SOP. Okay, that's the meaning of sum of products. So I have this expression here for the function F. I can easily draw a 2-level AND/OR circuit. So this will be a 2-level AND/OR circuit. So here the output of the first AND gate will be BD, and the output of the second one will be A prime, C, D prime. And then here I'm ORing. So my first level will be AND gates, and my second level will be just the 2-input OR gate. So that's a 2-level implementation, AND OR. Now I can easily convert this 2-level AND OR implementation into a NAND implementation. How to do this is easy. Well, the way to do it is that the first step is to insert bubbles. So in order to convert AND into NAND, I have to invert its output. So I'm going to insert a bubble, but if you insert a bubble, then this will change the function. In order not to change the function, you can have a second bubble on the same line. So by having 2 bubbles on the same line, it's like having 2 inverters on the same wire. They will cancel each other. Okay? So therefore, every time you insert a bubble at the output of an AND gate, then you have to insert another bubble on the same wire. So when you have 2 successive bubbles on the same line, on the same wire, then they will cancel each other. Like having just 2 inverters, one after the other on the same line, then they will cancel each other. Right. So now what we have done is that we have converted the first gate from AND to NAND. That's my first NAND gate. This is my second NAND gate. But the question is, what is this gate here? Okay, if you look at this gate here that has, it is an OR, but with inverted inputs. So what is an OR with inverted inputs?
NAND.
Exactly, it's in NAND. Thank you very much. So notice that here, for example, when I would like to draw an OR gate, this is an OR gate here, right? And I introduce bubbles at its inputs. It's like inverters. So if this is X, this is Y. Now the output will be X prime or Y prime. So what we have done is that we have inverted the inputs and then we OR. And when we invert the inputs and then we OR, using De Morgan's theorem, it will be the same thing as X and Y, everything is a prime. So what we can do is we can replace this gate here, this OR gate with inverted inputs with a NAND gate. So notice that now we have a pure NAND implementation. Okay, so we have converted the sum of product expression. Okay, we have converted the circuit, which was a 2-level AND OR implementation, into a pure NAND implementation. Okay, so this is known as NAND implementation. Any questions about this? Right. Let me show you how we can do it for NOR implementation. Now, in the case of NOR, rather than using a sum of products, we use a product of sums. So here I'm going to have a product of sums expression for the function g. So this is my function g, which is expressed as a product of sums. Okay, so these actually are sum terms, which are OR terms. And then when I take the product, it means I'm taking the ending of these OR terms. Now, if you have a product of sums expression, you can draw a 2-level OR AND circuit. So this is my 2-level OR AND circuit. Notice that the output of the first OR gate will be A or D. The output of the second 3-input OR gate will be B or C or D prime. And I need an AND gate here at the output to AND these 2 OR terms. So this is known as a 2-level OR AND implementation. So my first level will be OR gates, and my second level will be the AND gates. And my expression is called a product of sums expression. In fact, if you take any function f, you can express f, okay, either as a sum of products or you can express it as a product of sums. So there is more than one way to write the expression of a given function. Now, the reason why here I'm using a product of sums is that I would like to have a NOR implementation for this circuit. So in order to do that, we follow the same steps that we have done in the previous slide. So I'm going to insert bubbles. And remember that when you insert two successive bubbles on the same line, they will cancel each other. So here I have a bubble. Here I also have a bubble. So these are going to cancel each other. Here I have a bubble, and here I have another bubble, and they will cancel each other. Now, the reason why we put a bubble at the output of an OR gate is to make it NOR. That's basically the idea. So by having a bubble at the output of an OR gate, it becomes a NOR gate. So that's a NOR gate. This is now a NOR gate after inserting the bubble at the output. But how about this gate here? This is an AND gate that has inverted inputs. What do you think this gate is? So when you have here a gate, an AND gate, but the inputs are inverted. So suppose this is XY. What do you get at the output?
NOR gate.
It become NOR.
Exactly, it will come NOR. So this will be X prime and Y prime. And we know that X prime and Y prime will be not X or Y. Exactly. So this will become a two-input NOR gate. So we can replace this gate here with this one, with a two-input NOR gate. So now what I have is that I have a two-level NOR implementation. I'm using only NOR gates, okay, to implement the circuit. So rather than having a two-level OR AND, I have converted the two-level OR AND into a two-level NOR implementation. And the trick was very simple, just inserting bubbles on these two successive bubbles on the same line. They will cancel each other, and we can convert the gate. The OR was converted into a NOR, and the AND that has two inverted inputs is also converted into a NOR. Yes, questions?
What's the benefit of this? يعني ليش نخليها NOR?
Okay, because sometimes, okay, circuit designers prefer to use the NAND and the NOR over the AND and the OR. Okay, and the reason for that is that the NAND and the NOR can be implemented very efficiently using the CMOS technology. So NAND and NOR are gates. Okay, so NAND is a gate, NOR is a gate. Okay, and these gates can be implemented very efficiently in CMOS. In fact, we only need, in order to implement, let us say, a two-input NAND gate, we only need 4 transistors in the CMOS technology. If I would like to implement AND, sometimes people use a NAND followed by an inverter to implement the AND. So NAND is more efficient than the AND. And NOR is more efficient as a gate, okay? It's more efficient than the OR. So for this reason, people prefer to use these NAND and NOR gates over the AND and the OR. Do you understand this? So it's all about the cost of the circuit. So the implementation of these gates using transistors is very efficient. And this is why people like the NAND and the NOR gates. And they are also universal. Okay, so I can just implement my entire circuit using just NAND gates or NOR gates. Even here for the inverted input, for example, here I have D prime. It's not D, so really I have to insert an inverter, okay, to invert D to become D prime. But the inverter itself can be implemented using a NOR gate, a two-input NOR gate that connects to I can convert the two-input NOR gate into an inverter. So you see that I can actually have a pure circuit design, circuit implementation using only NOR gates. Okay. So remember that what we have seen in the previous slide here. Okay, so you have to start with the sum of products, a two-level AND OR to convert it into NAND, and you start with a two-level OR AND, which is correspond to a product of sum to convert it into NOR. Now, this does not really mean that you cannot really take, let us say, a sum of product and implement it using NOR gates. You can also do that, okay, but it would not be as efficient as the product of sums expression. Right. So this is the meaning here of the NOR implementation. Any other question about this? Right. I need to talk about the exclusive OR and the exclusive NOR. Now, exclusive OR and exclusive NOR are also gates that can be implemented using the CMOS technology. So let us understand these gates. Let me start first with the exclusive OR. Now, it's called exclusive OR because the output is one when exactly one of the inputs is equal to 1. So here, when you would like to take the exclusive OR of X XOR Y, notice that Y here is equal to a 1. Here, X is equal to a 1. Okay? So when you have exactly one of the inputs is equal to a 1, then the output will be equal to 1. Notice that when both inputs are 1 and 1, you get the output equal to 0, not 1. Okay? Because this is exclusive OR. So you have to have exactly one of the inputs is equal to 1, not both inputs. So this is the difference between OR and the exclusive OR. In the case of the OR, you get 1 when both 1, when either one or the other is 1 or both of them. Okay? But in the case of the exclusive OR, it has to be exclusive OR. It has to be exactly one of the inputs should be equal to a 1. Is this clear? This is basically the truth table of the exclusive OR. In the case of the exclusive NOR, it is just the complement of the exclusive OR. Okay, so notice that in the case of the exclusive NOR, the output is equal to a 1 if both inputs are 0 and 0, or it is actually equal to 1 if both inputs are 1 and 1. So if the inputs are identical, we get 1. If the inputs are different, we get 0. That's the complement. If you look here at the truth table, so this is the exclusive OR, this is the exclusive NOR. So notice that the exclusive NOR column is just the complement of the exclusive OR. This is the gate symbol. So notice that here we have an additional arc here at the input to indicate this is not an OR. It looks like an OR, but there is actually an additional arc here indicating that this is exclusive OR. And in the case of the exclusive NOR, we add an extra bubble at the output to indicate that this is the complement of the exclusive OR. Okay, is this clear? So this is the meaning of exclusive OR and exclusive NOR. Now, if you look at the exclusive NOR, it's also known as equivalence, because if you look here at the truth table, when both inputs are 0 and 0, or both are 1 and 1, it means that the inputs are identical. You get the output is equal to 1. So the output equal to 1 when X is equal to Y. And for this reason, exclusive NOR is known as equivalence. Okay? Okay, please feel free to interrupt me if you have any question about this. Now, we have certain properties actually for the exclusive OR and the exclusive NOR. I'm going to talk about them in a minute. But first, let us think about the implementation. If I would like to look here at the exclusive OR, as we have seen in this slide. So if I would like to focus here on the midterms, this will be midterm 1, this will be midterm 2. That's for the exclusive OR. In the case of the exclusive NOR, this will be midterm 0. And this will be midterm 3, right? So these are the midterms. And if I would like to write the exclusive OR as a sum of products, I can write it as X. I can say X XOR Y. I can write it as a sum of products as XY prime or X prime Y. Now notice that XY prime, what is XY prime? What is this midterm? It's midterm what? It's 1, 0, right? So this must be midterm what?
2.
Exactly, midterm 2. And how about X prime Y? That will be midterm what?
1.
3.
Exactly. So it's midterm 1 or midterm 2. You can write them either way because OR is commutative. So you can write it as X prime Y or XY prime. It does not really matter. Okay, so here we have, this is for the exclusive OR. For the exclusive NOR, it is just the complement of the exclusive OR. Okay, so it is xy or x prime y prime according to the truth table. Now this is midterm what?
3.
Yes, thank you. And x prime y prime is midterm what?
0.
Yes, 0, 0, 0. Exactly. It's very simple. So that comes actually directly from the truth table of the exclusive OR and the exclusive NOR. Now, to implement the exclusive OR and the exclusive NOR, they are called actually complex gates because they are more complex than the NAND and the NOR gate. You can implement it as a true gate, but I will not even go into the transistor level because this is beyond this course. So we can implement it as a single gate. Okay, so this is what people actually do, is that we have a true XOR gate or an exclusive NOR gate, but it is more complex than the NAND and the NOR. Or you can implement XOR and exclusive NOR by interconnecting other gate types. For example, to implement the XOR, I can implement it using AND and OR. So I can use here 2 AND gates and an OR gate. So basically, I can implement it as a circuit. But this will not be efficient. So for this reason, people can implement the XOR and the exclusive NOR as a true gate. So we're going to deal with it as a true gate. Now, because they are complex gates, the XOR and the exclusive NOR only exist for 2 inputs. They do not exist for more than 2 inputs. Okay, so they are designed for just for 2 inputs. If you would like to have a 3 input, okay, if you would like to XOR 3 inputs, we use 2 input XOR gates. So if I would like to say X XOR Y XOR XOR Z, so if I have here 3 inputs X, Y, Z, and I would like to XOR them, I need 2 input XOR gates. So I can take X XOR Y and then the result XOR Z. And the reason why is that if you look at the cost of a 3 input XOR gate, it becomes more expensive. Okay, and it is greater than the cost of 2 XOR gates. So for this reason, people use only XOR gates that have only 2 inputs because their cost is going to increase. Okay, when you increase the number of inputs. Now, the XOR itself and the exclusive NOR, okay, are associative. So therefore, you can easily put them in any order that you want. And this actually can mean that you can easily use, okay, 2 input XOR gates to implement larger functions. Now, why do I talk about the XOR and the exclusive NOR? They are very useful gates. I talk about them because we use them to design adders and subtractors. So I can use them actually in arithmetic circuits, also in multipliers. We use them in counters, we use them in incrementers, decrementers, so we use them in many circuits. Today I will talk also about parity generators and checkers. So we also use them, okay, to generate the parity bit and also to check the parity bit, so they actually are very useful in that case. Okay. Now let us talk about the properties of the XOR and the exclusive NOR. If I take X, any value of X, and I XOR it with 0, I'm going to get X. Remember that X here is a Boolean variable. Okay, so it can be either 0 or 1. So if X equal to 0, so 0 XOR 0 will give you 0. It will give you X. And if X is equal to 1, then 1 XOR 0 will give you 1. It will also give you X. So in general, X XOR 0 is always equal to X, regardless of the value of X. Right, if you look here at X XOR 1, it will give you X prime. It will give you the complement of X. For example, if X equal to 0, then 0 XOR 1 will give you 1, which is the complement of 0. And if X is equal to 1, 1 XOR 1 will give you 0, which is the complement of 1. Okay, so you can see that X XOR 1 will give you X prime. If you take X and XOR it with itself, you will always get 0. Why? Because 0 XOR 0 will give you 0, and 1 XOR 1 is also equal to 0. If you take X XOR X prime, you will always get 1, because if X equal to 0 and you XOR it with 1, you will get 1. If X is equal to 1 and you XOR it with 0, you will also get 1. XOR is commutative, so it does not really matter whether you write it as X XOR Y or Y XOR X. It does not really matter. Now, the interesting thing here is that if both inputs are complemented, so if you XOR X prime with Y prime, you get the result as X XOR Y. So if both inputs are complemented, you can remove, okay, the two inverted inputs, and you just actually XOR X with Y. Now, this can be proved easily with the truth table. You can just look at X prime XOR Y prime. You can look at the column of X XOR Y, and you can show, you can prove it that this property is, you can prove this property, okay? What's interesting also is that when you take the exclusive NOR, okay, of X XOR Y is the same thing as X prime XOR Y and the same thing as X XOR Y prime. Yani in other words, if I have, okay, this XOR gate, this is XOR gate. Now this is X, which is complemented. So let me put here X prime, and this is Y. The output here will be X prime XOR Y, correct? Now this will be equivalent to another gate, the exclusive NOR gate, and this is XY. So basically you can remove this prime and you can insert the bubble at the output. So this will be X XOR Y prime. So in other words, let me just, okay, insert here an inverter. Let me just remove this wire, just 1 second. So let me here, let us say, put an inverter. So when you invert one of the inputs, so this will be X prime, okay? So when you invert one of the inputs, you can remove this inverter from the input to the output, and you can actually introduce a bubble at the output. So this will work actually for exclusive OR and for exclusive NOR. So if one of the inputs is inverted, so when you have, for example, X prime XOR Y, it's the same thing as replacing it with the exclusive NOR of X and Y, okay? The same thing can be said if Y is inverted. If you invert both of them, if you invert X and Y, when you take the exclusive OR of X prime XOR Y prime, you will simply get X XOR Y. Now, the exclusive NOR and the exclusive NOR are both associative operations. So when I say X XOR Y XOR Z, it's the same thing as X XOR Y XOR Z. So therefore, we can just write it like this. So it does not really matter in what order we do the XORing. The same thing can be said about exclusive NOR. So this is the exclusive NOR of X and Y. And then when you take the exclusive NOR with Z, it's the same thing if you change the order. And because you are taking here the complement twice, you can replace it here with X XOR Y XOR Z. So let me tell you this trick here. So what this means about this property is that, let us take a look here at the last one. So here if I have, let us say, this is an exclusive NOR gate. This is X, this is Y. So here it's actually here the complement. This is actually is the exclusive NOR. And then you take here this and take the exclusive NOR with Z. Now you can move this bubble here from the input to the output. So this means that these two circuits here are identical. This is X, this is Y, this is Z. Notice that what we have done is that we move this bubble from here to the output, and because we have so basically we are inverting the inverted output, you can get rid of this bubble. I'm sorry, I made a mistake here. I should remove this bubble here. It is just XOR gate. So basically, when you have an exclusive NOR followed by an exclusive NOR, you can convert it into XOR and XOR. So for this reason, I said that this will be equivalent to X XOR Y XOR Z. So you can remove these two bubbles if you have actually the output is inverted. So when you have exclusive NOR followed by an exclusive NOR, you can remove these two bubbles and it will be equivalent to exclusive OR followed by exclusive OR. Is this clear, students? You have any question about this? So these are very important properties which are related to XOR and exclusive NOR, and we can actually use them, okay, to simplify circuits. when we are dealing actually circuits that involve, of course, the XOR and the exclusive NOR. So we have to remember these properties because we are going to encounter them later. Type. Questions? Everything is clear? Okay, let us move on. Let me talk about the odd function. What we have seen in the previous slide, we have seen the XOR and we have seen the exclusive NOR. But if you are dealing with functions that have more than 2 inputs, okay, let us say 3 inputs or 4 inputs, then we can define something which is called the odd function or something which is called the even function. So the meaning of an odd function, it's a function that its output is 1 if the number of ones is odd in the inputs. Yeah, for example, let us take a look at this function. Here, when you count the number of ones in the input, you have exactly a single one, which is here. So therefore, the total number of ones is odd. So therefore, we got here the output is odd. The same thing here, you have a single one. This is my 1. So it is odd. The number of ones is odd. So the important thing is that the number of ones is odd in the inputs. Sorry. That's okay. So that's the number of ones is odd in the inputs. Okay, so here you get actually also a 1. Here, because we have 2 ones, the output is 0. Why? Because that 2 is an even number. So when the number of ones is even in the inputs, you get the output equal to 0. Here I have a single one, which is odd. So therefore, we get the output is equal to 1. Here I have 3 ones. If you look at the last entry, we have 3 ones. And 3 is an odd number. So therefore, the output is also equal to 1. So when you have 2, which is even, you get 0. Here I have 2, which is even, you get 0. So this is the meaning of the odd function. Now, if you would like to look at the minterms here, this will be minterm what? This is minterm
1.
Yes. How about this one?
2.
How about this one?
4.
And
7.
thank you. So I can always write this function in sigma notation. So it's the sum of these 4 minterms. And I can write it algebraically. So this will be minterm 1. That will be x prime y prime z. This will be minterm 2, which is basically x prime y z prime. This will be minterm 4. And this will be minterm 7. So we can write it algebraically. Now notice that if you write it as a sum of minterms, let me write here SOM here, sum of minterms. It will be long, will have 12 literals. So really, the expression is very long. You can use, actually, you need 4 AND gates. Each AND gate must have 3 inputs, and you need a large 4-input OR gate to implement this odd function. So really, this function is really complex to be implemented. But if you think about XOR gates, okay, when you think about XOR gates, now the XOR gate itself implements an odd function. So I can write it as X XOR Y XOR Z. Let me take you back, okay, to the XOR gate. Okay, let me take you back here to the XOR gate. So notice when I take here X XOR Y, notice that here the number of ones is odd. You get the output equal to 1. And when it's even, we got 0. Here we got, when you have 2 ones, we got 0. So for this reason here, you can see that when you have 2 ones, you got 0. When you have a single one, you get 1. So XOR is an odd function. But this XOR is for 2 inputs. So the meaning of odd function is that if you would like to go beyond 2 inputs, let us say 3 inputs, count the total number of ones. So when you take X XOR Y XOR Z, this will give you 1 if you have the total number of ones is odd. So this is why we can easily implement the odd function using XOR gates. That's the main advantage of the odd function, is that, I mean, this is the main advantage of the XOR gates, is that we can use them to implement odd functions. And I can draw the circuit diagram like this. All what I need is just 2 XOR gates. So X XOR Y XOR Z, and the output will be the odd function. Okay. if I have, let us say, a 4-input odd function, if I have w, x, y, z, then I will say that the f odd will be w XOR y, sorry, w XOR x, XOR y, XOR z. So I will need 3 2-input XOR gates. If you look at it as a sum of minterms, it will be very long and very complex. So this is the importance of the XOR gate. We can use them to implement odd functions. Right, so this is the meaning of the odd function. As I said, you can interrupt me at any point if you have questions. I also have the even function. Now, the even function is just the complement of the odd function. And rather than counting the number of, so rather than saying the number of ones is odd, we say that the number of ones is even. Okay, so if the total number of ones is even in the inputs, then the output will be equal to 1. So notice that here, this is a function of 4 variables. So if you count the number of ones, there are 0 ones, and 0 is even. So we say that the output is 1. Here we have a single one, which is odd, so the output is 0. Here I have a single one, so the output is 0. Here I have 2 ones. 2 is even, so the output is equal to 1. Okay? And then we can continue. So here I have 2 ones. So that's even. Here I have 2 ones. That's even. Here I have 4 ones at the bottom here, the last entry. So that's even. So we got a 1. I can write this in sigma notation. What are the minterms? Can you tell me what are the minterms for this function? Even. We have minterm 0 here, right? What are the other minterms? What
3.
Is this? Yes. What is this one?
5.
Yes. This one.
6.
Excellent. Next one.
9.
Yes.
10.
Yes. So it's really easy. How about this one?
12.
Yes. Yes.
And
how about this
15.
one?
15.
Exactly. Minterm 15. So I can write it in sigma notation. This is here actually my sigma notation. It's the sum of these minterms. Now notice that if I would like to draw the odd function for this 4 variable, it will be just the complement of the even. Okay, so one is the complement of the other. Okay, so the complement, if you would like to say f prime even, it will be f odd. So f odd is f prime even. Okay, too many emails. Fine. So if you want to write it as a long expression, as a sum of products, well, we have here 8 minterms. These, if you count them, these are 8, and each minterm will have 4 literals. So 8 multiplied by 4 will give you 32 literals. It will be really a long expression. But the nice thing about the XOR and the exclusive NOR is that they are meant to be used by odd and even functions. So here I can write it as, okay, W XOR X, XOR Y, XOR Z, but this will give me F odd. If you look inside the parentheses, this is F odd. So what we have to do is that we have to complement the F odd to get the F even. So this is why we have this prime here. It means the complement of the F odd. Now the way to implement this is that we can implement it using XOR gates. So this is here, the output will be, so I need actually these 2 XOR gates. I will get here the output W XOR X. Here I'm going to get Y XOR Z. But then finally, what I need to do is that I need to XOR and then complement. So the last gate is an exclusive NOR. And the reason why we have this exclusive NOR is that we need to obtain the F even, not the F odd. If I remove this bubble at the end, if I just use XOR, it will give me F odd. But the last gate has to be an exclusive NOR to get the F even, because the F even is just the complement of the F odd. So notice how we have implemented this even function using 2 XOR gates and 1 exclusive NOR gate. Okay. So is this clear? As I said, we are going to encounter these XOR gates and exclusive NOR, okay, later when I design, let us say, adders. Okay, we are going to see them in arithmetic circuits because they are very useful. Now, one application of XOR and exclusive NOR is parity generators and parity checkers. Remember the concept of parity? I talked about it at the beginning of the semester. So here we have a sender and we have a receiver. And the sender here is going to send an n-bit code. For example, n, if n is a character, it could be an 8-bit code, okay? So, so suppose that the sender would like to send this n-bit code to the receiver. Now, the sender is going to use a parity generator to generate an extra bit. This is my extra bit, and this is the parity bit. So it's going to send the n bits plus an extra parity bit to the receiver. The receiver is going to receive n plus 1 bits, and then it's going to use a parity checker here to check if there is an error in the received code or there is no error. So here, if there is an error, then this out will be equal to 1. Otherwise, the out will be equal to 0. Now, if there is no error, the receiver can remove the parity bit and keep the n-bit code. Okay. So the reason why we have this parity bit is just for checking for errors in the transmitted data. Okay, so we can use two types of parity. We can use odd parity or we can use even parity. Now, suppose that we would like to use odd parity. Okay, so if I would like to use here odd parity, then the total count of ones in the transmitted data here in the n plus 1 bit code, it must be odd. That's the meaning of odd parity. Count the total number of ones in the transmitted code. This total number of ones should be odd. Now the sender wants to send an n-bit code, and it has to generate an extra bit to make it n plus 1 bit code. Now, in order to generate this odd parity bit, the sender is going to use an even function. So an even function will be used to generate the parity bit. Why the even function? Well, we would like to have the total number of ones to be odd. But if the total number of ones here is odd, okay, the even function will give me a 0 parity bit. If the number of ones in the n-bit code is even, then the parity bit will be equal to 1 to make the total number of ones in the n plus 1 bit code to become odd. So for this reason, we use the even function. So the function must be even. I have an example about this in the next slide. So whenever you have, and if you would like to use odd parity, you have to use an even function to generate the odd parity bit. But that's for the sender. How about the receiver? The receiver is going to receive n plus 1 bit code. This is my receiver here. And this is the parity checker. So the parity checker is going to check the n plus 1 bits. It wants to check if there is an error in the received, okay, n plus 1 bits. The receiver is going to also use an even function to check the n plus 1 bits. Now, if it receives an even number of ones, that's a clear indication that there is an error. So the meaning of the even function is that the parity checker is going to count the number of ones. And if the number of ones is even, then it's going to produce 1. So the error will be equal to 1. So for this reason, we use an even function to detect the error. If the total number of ones is odd, then there is no error. So the even function will give me 0. So for this reason, we use an even function in the parity checker. So that's if we would like to use odd parity on the sender and the receiver side, the even function should generate the parity bit, and the even function should be used to check the parity. Right. What about if I would like to use even parity? It means that the count of ones in the n plus 1 bit code should be even. In order to generate the parity bit and to check for the parity bit, we must use an odd function. So notice that we are using just the opposite. So in the case of odd parity, we use an even function. In the case of even parity, we use an odd function. So we are just using the opposite, okay, to generate the parity bit and also to check if there is an error in the received data. Right, here's an example. Suppose I would like to design an even parity generator So now here my parity generator and my parity checker will be for even parity. As we have seen in this slide, in the previous slide, for even parity, I have to use an odd function to generate the parity bit, and also I have to use an odd function to check. So the parity generator and the parity checker are going to use odd functions. Right, so I would like to use even parity for 3-bit codes. So therefore, okay, the solution would be very simple. We use a 3-bit odd function because we have only 3 bits. So here there is the sender is going to send 3 bits, X, Y, and Z. These are my 3 bits. And is going to use an odd function to generate this parity bit. So the parity bit is called P, and we are going to use even parity. So the reason why we use an odd function, because if you have the total number of ones in the XYZ, if we have them odd, then the parity bit will also be 1, so that we make the total number of ones, including the parity bit, we make them even. Okay? That's the solution for the parity generator. Now, for the receiver, the parity checker in the receiver side is going to receive the parity bit in addition to XYZ. So it's going to receive 4 bits, the XYZ plus the extra parity bit that was sent by the sender. Again, we're going to use a 4-bit odd function, okay, to check if there is an error or not. So this is going to produce an error if the total number of ones is odd, because it's supposed to receive even number of ones, because we are using even parity. Right. So for this reason, we use a 4-bit odd function. So notice that in the case of the parity generator and the parity checker, we are using just XOR gates to implement the odd function, and the parity generator and the parity checker. I have an example about this. Suppose that XYZ is equal to 0, 0, 1. Okay. So XYZ equal to 0, 0, 1, then we are using an odd function, then the parity bit must be equal to 1. Because we have here the number of ones is odd, then the parity bit must be equal to 1 to make it even, because we would like to have a total number of ones to be even. So therefore, the parity bit should be equal to 1, so that now the transmitted data will be, the parity bit is here is 1, and this is my data XYZ. So in total, we have an even number of ones. So now the sender is going to transmit the parity bit, and the XYZ is going to transmit 1, 0, 0, 1. Okay. At the receiver side, the receiver should receive 1, 0, 0, 1. But suppose that while we are transmitting 1, 0, 0, 1, one of the bits flipped. It does not really matter which one. Any bit can be flipped. Okay, there can be an error in any one of these bits. So at the receiver side, suppose that Y, this bit Y here, changes from 0 to 1, okay, because of some noise in the transmission line, whatever reason, okay? So now the receiver is going to receive 1, 0, 1, 1. So clearly we have an error. So for this reason, the parity checker here is going to use also an odd function to check the received number of bits. So if the received number of bits is equal to odd, then the error will be equal to 1, indicating that it has detected an error, because it is supposed to receive an even number of ones, but it received an odd number of ones, and this is the indication of the error.